Martingale is a stochastic process with these two properties. So basically, it is technical condition that mean exists, expected value exists, and then your expectation of xn plus 1 of a future value conditional on past data. You can regard it as the data. Okay? Historical data is actually the most least value. That's simple. So suppose you have, of course, you can obtain the historical data of IBM yesterday, today, before yesterday, like 10 years historical data, and based on that, you want to estimate what is tomorrow's IBM price, and then if IBM stock price follows Martingale, your expectation about tomorrow's IBM stock price is what? Yes, it should be today's IBM stock price. This is actually not a, it sounds a bit strange, but it is actually not that unrealistic. This kind of property is sometimes called, version of this story is sometimes called efficient market hypothesis, EMH, and actually it is a weak form efficient market hypothesis. Weak form efficient market hypothesis says that you cannot actually make money based on the historical, by analyzing historical data. Historical data does not contain much information. And then we defined Martingale with respect to other process here. And then you can regard this one as like your information set. Y is your information set. So from Y0, Y, so you have data from Y0 to Yn, then it means you accumulated information from time 0 to time n. And then based on that set of information, your expectation about next period stock price is today's stock price. Something like that. Then I think it would be nice to have a review. Let's say y0, xn is y0 plus y1 plus yn. And then let we set x0 is 0. No. X, yes, x0 is 0 and it should be from start 1. And expected value of y, I, is all 0. And then, actually this is I think enough. If mean exists, it is always less than infinity. So, if those y process are independent, if they're independent random variables, then last week I showed that xn is Martingale. So this is like, you can regard xn is stock price, xn is stock price, and each yn, yi is kind of return per day. So if you accumulate return per day, day by day, then it is the, from some time, then it should be stock price, right? Today's stock price is stock price 1 week ago plus everyday return for the last 1 week. Then I showed that this is Martingale, and then I think 지난 시간에 왔었나? 주제와 Please come forward and prove this is Martingale. Come forward. No, don't look at the note. Please come forward. Try. Okay, I'll give you a hint. You can use this definition of the martingale. Please, quick. Yeah? I don't like hanging around there. You have to move quickly. Okay, try. You have to prove that xn is martingale. The process of xn is martingale. So that is the definition. I think it would be a good idea write down this one first. Why don't you write down this one? Okay, and our goal is to that is xn, right? And then write down equal. And then, no, delete that. And then we decompose xn plus 1 into old part and new. Xn plus 1 is basically xn plus yn plus 1. Right? And then we know xn. Up to xn is old part, and yn plus 1 is new part, right? Okay, so xn plus 1 is xn plus, no, plus yn plus 1, right? And then conditional on the information up to the n. Right? Can you understand up to this part? You know, xn is sum from y1 to yn. So therefore, xn plus 1 is a sum from y1 to yn plus 1. Therefore, xn plus 1 is xn plus yn plus. Do you understand that part? Not exactly. Okay. Write down x plus 1. Okay. So x plus 1 is no. X, okay, xn plus 1. Sorry. Xn plus 1 equal should be what? Equal from y1 to some y1 to yn plus 1, right? Okay, write down yn plus yn plus 1, okay? And what is y1 from summation of y from y1 to yn? What is that part? yet, but given the definition. Okay, to apply this one, okay. Then what is this part? Yes. Yeah, that's why we wrote down xn plus 1 conditional on history of xn is xn plus yn plus 1, something like that. It's a tree. Okay, we are decomposing stock price into the known part and unknown part. We do not mix known and unknown part. Okay, we want to separate. It is important to know what we know and what we don't know. Socrates, 너 자신을 알라. Know yourself. It means what Socrates really means by saying you have to know yourself is that you have to know what you know and what you don't know. No, it is not over. You have to return your seat when I allow you to do so, okay? Equals, not over, okay? And now, given this part, okay, you have to solve this. So equal. Now this is summation, so you separate this part and this part for each expectation. Yeah. So it is sum of two expectations, right? No, you shouldn't forget equal sign. It is equal to what? The sum of this part and this part. Yeah. No, it is not sum. It is just a set. Okay? In mathematics, notation is very important. And then we solve for first, what is the first part? What is the expected value of xn conditional on x0 to xn? That should be xn, right? Because xn is already in the information set. So first part is to the xn. Okay, so write down. Yeah. It should be right. Do you know why? Why they should be xn? First part is xn. Okay. Again, what should be the second part? What is yn plus 1 conditional on x0 to x0? y0. Yes, right. Why it is 0? It's 0, yeah. But it is the unconditional expectation and that is conditional expectation. So why that one and that one should be same? Right? There is no conditional part. That one has a conditional part. But why should be 0? Because no No connection? What do you mean by they have no connection? Why? What does that mean? What is the connection? 한국말로 해봐. 커넥션이 어떻게? 서로 확률이 영향을 준답니다. 왜냐면 because they are independent. Basically, x is a sum of y. X is a sum of y, and each y is independent. So x and y past x and x collection of x0 to xn should be independent of y n plus 1 because it's independent definition of independent, right? So it is 0. Yeah. So okay, so let me 0. So actually we prove that x is indeed martingale now. Of course you didn't show this first part, but it is not that important. But that is important. So okay, so why this and now why this one and this one is the same? There is no end to the p. So okay, go back to your price. Again, you have to go back to your condition definition, conditional information. This is conditional on this information. We want to know x n plus 1. And again, this is in the information set already. So we know this value. So it is constant. Expectation of constant is that constant, right? It is not stochastic anymore because we know the value of xn. It is like what is the expected value of stock price of Samsung Electronics yesterday stock price given the information that I have data of Samsung Electronics stock price from yesterday to like 1 year ago, right? It is like same problem. Okay, I'm not asking something new. I'm asking what is the stock price of yesterday given that you already know, already have the data about yesterday Samsung's price and others. So we can be a bit intuitive. I mean, it is kind of mathematics, but basically it is not a mathematics. It is in some sense all logical statement. It is like a story. So sum of independent, basically sum of independent random variable is martingale. Kind of all. Of course, if expectation is not 0, it is not martingale. But if it is some sort of constant, we can subtract the constant from this one and define as a new random variable, and they become martingale. So in some sense, the sum of independent random variable is kind of version of martingale. Not only sum of independent random variable, but also, so this is a proof. Yeah. Where is it? Yeah. The variance of a sum is also kind of version of martingale. Okay, so last week I showed that this xn process now it is a sum of a square minus n sigma square, variance minus n. If you divide this one with n, then it is actually sigma square, and it is kind of definition of variance, and it is variance. Of course, it is not exactly, it is definition of sample variance in some sense. Sample variance and sigma square, and we are simply multiplying n to that part. And today we have another very important martingale, which is Dooves martingale process. So now let's assume that, let's say that sequence of y0, yn, y2, blah blah blah, sequence of y, be an arbitrary sequence of random variables. So it is stochastic process. Okay, it's a sequence of random variables, collection of random variables with indexed with time. So it is a stochastic process. So y0, yn is arbitrary stochastic process. And then suppose x is a random variable satisfying technical condition. So let's say x is some sort of like a true value of the stock price, true value of the Samsung Electronics, true value of Apple. Yeah? No one knows the true value of the Apple stock price, right? The fair value of the Apple, no one knows that. But there, we can say that at least it exists. Okay. We can say the true value of the apple exists. We can say that like this. It is less than infinity. Right? You know, apple shouldn't be more valuable than the value of United States, maybe. Right? So at least it exists. So Apple's value, true value, satisfies the technical condition. And then we can form our valuation. You can do the valuation. You learn the corporate finance and using your knowledge about corporate finance. And then you can do the valuation about Apple. Of course, in order to do the valuation, you need not only technical tool like a net present value model, you also need some data. Right? And let's say you have data. You accumulate your data from time 0 to time n. Okay, so for the last n days, you accumulated your data, and maybe tomorrow you have more data. Samsung introduced new mobile phone, and then Samsung is competitor over Apple. So you have new information. So you have to update your valuation on Apple. So Excel is that kind of process. Every day, okay. As time goes by, you have new information. You keep updating your valuation of Apple. Okay? So X1, X0 is your valuation of Apple at day 0. X1 is your valuation at time 1. At that time, you have information of Y0 and Y1. And Xn is your valuation on Apple at time n. And at time n, you have more information like this. Information you accumulated from Y0 to Yn. And this kind of valuation process, your valuation on Apple every day, that is called Dooves process. And that Dooves process is also martingale. Very interesting, right? Suppose x is a random variable satisfying that technical condition, then xn is conditional expectation of x conditional on your information up to time n, and let's call it xn. Then xn forms a martingale with respect to your information set. And xn is called the Dooves process, and Dooves process is martingale. First, let us check technical condition. Technical condition that expected value of absolute value of xn should be less than infinity. Let's see that. So, expectation of absolute value of xn. And xn, by definition, xn is your valuation of x, conditional your information, right? And then there's a trick. So there is absolute value outside of expectation, and we can put expectation inside of the expectation, right? Second expectation. Yeah. So we put this one over here. Then expectation of absolute value should be greater than absolute value of expectation, right? Naturally. Therefore, we have less than equal over here. And then this one is the same because law of iterative expectation. Right? We take expectation with more information, and then we take expectation again with less information. Then given less information, this information is not available yet, so we can combine expectation together with less information. Okay, so it becomes like this. Okay, so we use a tower property, law of iterated expectation, 2 times from here to here and here to here. And by assumption, this is less than infinite, so it satisfies technical condition. Again, law of iterative expectation is very, very important. This is actually quite implicitly quite often used in practice, not only in academic or in university. This property is actually used a lot of times in industry as well, without knowing that they actually apply law of iterative expectation. I'll demonstrate that later. Okay, so we checked first condition. And then second part. Okay, second part. So expectation of xn plus 1 conditional on, okay, conditional on information from y0 to yn. So let's think about what it means. So it is expected value of the, so there is an Apple stock price, Apple's fair value, which is x, which is unknown, right? And xn is your valuation of Apple at time n, right? And xn plus 1 is your valuation on Apple tomorrow. Of course, you don't know what would be your valuation on Apple tomorrow, right? Because tomorrow you will have new information, so you will surely update your valuation on Apple. So you don't know what would be your valuation on Apple tomorrow at time n plus 1, right? You don't know that. But still, there is random variable, right? Still, there is random variable. Therefore, you can form expectation about your valuation on Apple tomorrow given your information set up to today. Okay? That's what this equation means. Okay. And then we use law of iterative expectation again. So in order to calculate what is your, in order to get expectation about what is your expectation, what is your valuation of Apple tomorrow, okay? Let's assume you are in tomorrow, okay? First, let's assume that you are already tomorrow, okay? So tomorrow you have information up to time n plus 1, right? You will have information up to n plus 1. And then basically your valuation xn plus 1 is by definition of your valuation on Apple tomorrow with the information accumulated up to tomorrow, this part. Okay. And then this one is basically, so from here to here is we are just using definition of xn plus 1. And then we have conditional part to so on. So it's like assuming that you are in tomorrow, okay? So is this part, now this part is like, what if you are already tomorrow, okay? Tomorrow you form expectation on Apple, about value of the Apple tomorrow. And then Given this one, now you think again, okay, about what would be your valuation on Apple tomorrow today. It is such a, I mean, it's a convoluted sort of concept. So sorry, I cannot explain it more easily. But I have to use the same word over and over, so it is confusing. So again, I mean, I want to explain more realistically. So this one is like assuming that suppose you have a time machine and you go to tomorrow and you have expectation, and now assuming that you are today. But actually you don't have a time machine, so it does not make sense that you go to tomorrow. So therefore, anyway, since you are today, you have information only up to today. Okay? So in the end, what you have is only information up to today. And it's like taking expectation on X with only information today. Okay? So this only same to this one. So again, I'm reiterating low iterative expectation, right? And then this one is Xn by definition. So it means that, okay, this means that, okay, so Xn is basically this one. Your expectation on your valuation tomorrow is same to your valuation on Apple given the information today. Right? It should be right. I think it is intuitive. So where your expectation, so given the information up to today, your expectation about your valuation of tomorrow should be same to your today's valuation. It should be, unless you are systematically making valuation error, it should be same. Okay? Your best guess about what would be your valuation tomorrow with more information should be your valuation today. Because your valuation today is your best guess given the current information set. So TUPS process is very important. We will use the TUPS process to solve more complicated problems. Any question? Isn't it fun? I think it is very fun. It is fun and interesting concepts. And nice review about your high school mathematics, about expectation and those things. Now we have a bit hard part, right? Martingale with respect to the sigma field. It is like a topology. Have you ever heard of a topology? Do we have anyone who visit mathematical or engineering department and took like real analysis or advanced calculus or topology? No? No one. 수학과 가서 과목 듣고 그래본 사람 없어요? 혹시? 여기 공부할 사람이 없구나. 박사학위에 관심 있고 이런 사람이 없구나. 어쨌든. 네. Anyway, it is another very interesting and exciting one. Kind of topology, real analysis. kind of. Did you learn real analysis in the engineering department? In your department? Real analysis? No. Okay. So you are also exchanges. By the way, last night I saw a bunch of exchange students clustered in front of business school, and they moved to hospital somewhere, like more than 20 exchange students. Was there a party yesterday? TLC. Okay. 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 I see. So there are a bunch of groups for exchange students. So you didn't go to the party yesterday. Oh, you have party tonight. So anyway, there are a lot of exchange students last night about 7 p.m. at night, and they look all happy and excited, and I can surely guess that they were about to have interesting party. They are all excited and all happy. So, wow, I envy them. So, does Hanyang University treat exchange students well? So, if you have any complaint, please let us know. Okay. So, did you go to the party yesterday? You did. Okay. What you did? Did you? You just talk? Nothing more. Nothing fun? Just talk? Where? Okay, where did you talk? Okay, actually that's another very interesting example of Martingale. What I mean is that suppose there was a party in exchange student in front of Wangsimli station. So this is Wangsimli. This is Wangsimli. And suppose this is Wangsimli station. Let's assume that bunch of exchange students had a nice, very nice time, and they drank a lot. They consumed a lot of alcohol. And Felix was particularly drunk. Let's assume that. So let's assume that this is Felix here. And then exchange students now, the party is over in front of the Wangsimli station, and they say goodbye to each other, and they all went home. And then about 1 hour later, now someone called, there is a news. Okay, let's assume that now 1 hour later, after they say goodbye to each other, there is a news that Felix is missing. Felix was kind of overwhelmingly drunk, and he's simply missing. So we don't know where he went, right? No idea. So the goal of the exchange students now, we have to find Felix. He's completely drunk, and he's missing. So we have to find. So question is, where should we start? Where should we start from finding, in which part, okay? Where should we start searching for Felix, okay? If he's missing, okay? Restroom? He is not feeling well, so maybe restroom, yeah? But thing is that Felix is completely drunk, so I don't think he can find the restroom either. His movement is completely random. So where should we start searching for him in that case? So his movement is completely random. The answer is right here, the most least location of Felix. Because Felix's movement is Martingale, isn't it? Because because he is completely drunken, so probability of his movement to this participant all same. Right? So in expectation, since his movement, his probability of movement is same to every direction. So in expectation, his place is like this. Right? So completely independent. Therefore, we should. So given our information, so maybe we have history about the personality, about the information about his girlfriend or whatever for the last 1 year. But because he's completely drunken and his movement is Martingale, we should start searching for him right here, the most least place of his presence. Right? This is one application of Martingale. So anyway, yeah. let's go to the martingale with respect to sigma field. Let's assume that omega, this is omega, in Greek capital letter omega, and Fp is called probability space. This is one way of defining probability. Okay? Actually, let's review about our high school math again. Okay, in high school, okay, please refresh your memory. Okay? What is probability? What is 확률? What would be the high school answer for probability? High school answer for the definition of probability. We have to exactly know the definition of probability first. What is the definition of probability? Exact definition. Germans like exactness, right? That's German thing, like exact, precise, and rigorous. So what is the exact answer for probability? Yeah. Right. So you have to define with something else. Yeah. Maybe it's not in high school textbook. Maybe it's not in German high school textbook. In Korea, we have like for high school, we have like 10 kinds of high school textbook for mathematics. And I checked one by one, and only 2 of them describe the exact definition of probability, actually. Only 2. So I was so disappointed with the author of the high school mathematics textbook. Anyway, what is your answer? Yeah, try to describe. So you can generate your own definition. Right.
Describe how often they will happen given
How often?
X experience.
How often? Okay. How often does it happen? This is one possible answer. Any other answer? Right. What is the Chinese way of defining Chinese way of defining probability? What is probability? Beg your pardon?
It's so dark, so your seat behind the road, so it's sleep.
Okay. I think it is definitely Chinese definition is too hard to understand for me. Anyway, what is the Mexican definition of what is probability?
It's a function, sample space.
Okay. So definitely you learned it, right? Oh, yeah. You are good. You have very good start. Okay. Function from sample space and 0 to 1. Yeah, definitely. This is the right answer. Where did you learn the definition? That definition? Mexico. Okay. High school or Mexican university? University. Okay. That's the definition. So let's check Wikipedia. Okay. Probability. Probability measure of likeliness that an event will occur. This is nonsense, right? What is likeliness? Likeliness is probability, right? So it is a tautology. It is not informative definition ever. Probability used to quantify an attitude of mind towards some proposition whose truth we are not certain. Oh, it is a Bayesian definition of probability. You know, there are basically 2 ways of defining probability, like Bayesian or classical way. But for the purpose of this class, let's take an axiomatic approach, So I think there should be somewhere Huygens and wow. There are too much information. Okay, so mathematical treatment. No, this is not. Probability action. Right, okay. In 콜목으로 axiomatic approach, so we have a more intuitive approach. Like for classical thing, like when we say probability of, when we throw a coin, the probability of head and tail, both of them are half and half. One classical approach of defining that probability of head is 1/2 is that we throw coin like 100 times, and approximately 50 times of them is like head, so we define it like 1/2, something like that. That's like a classical approach. Then the critique on the classical approach is that it is never exactly same to 0.5. It converges to 0.5, but if we throw coin 100 times, it is not likely that exactly 50 times would be head, right? It is not likely. Not likely. If we throw coin 1,000 times, it is even less likely that head is exactly 500 times. It is even less likely. So there is a vague, right, ambiguity in the definition of classical approach. In the Bayesian approach is some different. Bayesian approach is that we don't have to draw. We just believe. We just believe that probability head is 1/2 because, well, if that coin is fair, then probability head or tail is both equally likely. Therefore, probability head should be 1/2, something like that. This is like more Bayesian approach. And then more general approach, which is the probability action, is like we have exact mathematical definition. In mathematical definition, we define probability as a function, as Felix mentioned. Probability is a function and it satisfies 3 conditions. If it satisfies 3 conditions, it is a probability. Then actually it's not condition, it is kind of axiom. It satisfies 3 axioms, we call it probability. Axiom 1, okay? Axiom 1 is probability is the basically function with non-negative number. So there is now nothing like a probability of minus 0.3. There is no such thing because by axiom, probability should be always positive. So first axiom is probabilities should be positive always. Now second axiom is that, okay, we have to define sample space, but the probability something happens, okay, is 1. So probability of an entire set is 1. So basically, so from this definition, we can get the probability function, basically a function from some set to the real number. Okay. So again, that's important. From second axiom, we can get the probability the function. So domain is a set. Okay, and then what is domain and why? What is that? Range. Range is real number. Range is real number between 0 and 1. Right? It should be always positive. And then whatever happens, the function for entire domain is 1, so it shouldn't be greater than 1. So basically probability function from a set to the real number and real number between 0 and 1. Okay. Like dice. Let's try dice. Okay. 주사위. In the dice, let's assume that it is very fair dice. If it is fair dice, then what is the probability of, so 1, 2, 3, meaning then the probability that either 1 or 2, 3 occur, what is that? Yeah, yeah, 50%, right? 1/2. Okay, so this is an example, right? So this is a function, and then domain is set. either 1, 2, 3. And the range is 1/2. It is between 0 and 1. So it is a probability. Okay. Third axiom is any countable sequence of disjoint event is satisfies this one. So probability that either this one and this one occurs is sum of each probability under the assumption that they are disjoint. There is no intersection. So it is like a probability of 1 for dice union probability of 3 is what? If we use that, if it is truly probability, it should satisfy third axiom. And third axiom says that if they are disjoint, and we can separate it with summation. And indeed, if you draw dice, 1 and 3 cannot occur simultaneously. If they occur simultaneously, that would be very interesting dice. Right? So there is no intersection, so it is 1, it is 3, right? And then if you go to the fair, it is 1, 6, 1, 6, and then 1/3. Right? So probability is basically a function that satisfies these three definitions. It is very important, and I think it is important to know this one. And you should be taught in high school. Probability should be taught in this way. Otherwise, it is very confusing. You know, in high school mathematics, I mean, 확률 통계, the probability and statistics part is the very last part of the mathematics, right? 문과, 이과 마찬가지로. So in high school mathematics, this probability and statistics is the very last part. And in the university entrance exam, there is usually 1 or 2 problems from the section. So to some students, maybe it is wise to entirely ignore that part, right? Instead of investing your time to study probability statistics, you can simply give up that 1 or 2 problem in university test, and instead you can randomly select, and who knows, you are lucky, right? And I know many students do that. And then in addition, in high school textbook, probability and statistics is not well written. Most of the textbook, it is not well written. And I think because it is not from the real definition correctly. If it is started from real definition correctly, it is logical. Every step it is logical. So it is very easy to understand. Actually, that part is easier than other part. Anyway, so probability is this one. Probability function that satisfies these 3 actions. And then let's go back to our one. And then we have slightly more. Basically, what I'm going to say right now is similar story. Okay, Martingale with respect to sigma field. Okay, we are about to define Martingale with respect to sigma field. Okay, this is the special case of this one. Okay, we defined Martingale with respect to arbitrary stochastic process, right? So in this case, xn plus 1 condition y0 to yn is xn. Okay, so this is arbitrary process, and I'm about to say that this now it is not arbitrary process anymore. This is y0 to yn is a sigma field. Sigma field is a kind of stochastic process with some structure, more similar to information that we know. Okay? I implicitly mentioned that y0 to yn, history y0 to yn, some sort of information relevant to the xn. But if we give some structure called the sigma field into this, then it is really similar to some sort of information. Okay? So this is Martingale with respect to y, and I'm about to define Martingale with respect to sigma field. And again, sigma field is special case of this special case of stochastic process. And before doing that, okay, we have to know probability space. We already learned probability, okay? Yeah. And this triple, FP called, this triple is called probability space. This probability space is like a major theoretical approach of defining probability actually. So here, let's start from familiar one, P. This is a probability function that we define. P is the function, P is the probability that satisfies that three action. Okay, something you know. And another one, okay? This omega is called the sample space. The sample space of that omega whose element, small omega, corresponds to possible outcomes of an experiment. Possible outcomes of experiment. So, okay. Let's go back to our dice example. When you draw dice, what are the possible outcomes? 1, 2, 3, 4, 5, 6. That is omega, okay? Okay, that is omega. So 1, 2, 3, 4, 5, 6. So omega is 1, 2, 6. That is omega. Very easy, right? So this is what we already learned. So that's why P is the function from this sample space to real number between 0 and 1. Okay? And this weird part, F. F is called the family of event. It is a collection of sets. A collection F is F, but is Professor Oyang is not good. I'll show you more beautiful F. So this F is, yeah, this F, right? Now it looks more beautiful, right? This F, a set of events. So F, this F. So we have to distinguish this F from the usual English because in mathematics, in order not to be confused, right? I don't know how to call this F, but it is F, but it is a calligraphic F, some sort of, I don't know. Yeah. So F is a set of events. Set of events, and you can say F is all the possible subset of sample space. Okay? So, of course, possible outcome, when you draw coin, possible outcome is 1, 2, 3, 4, 5, 6, right? That is possible outcome. But possible event is different. Possible event is different. It depends on how you define the event. If you define the event like odd number or even number, what is the probability of an odd number when you draw dice? 1/2, right? Odd number is 1, 3, 5. So that is kind of subset, right? That is kind of subset. Odd number 1, 3, 5. That odd number, and then probability of that odd number is 1/2. So the event is like all the possible subset of, not all the possible subset of omega, and there's a possible event. So a set of events where each event is a set containing 0 or more outcome. Okay. Where is it? So family of events is slightly, it is the same meaning. The family of events or collection for subset A of sigma, we said the event A occurs if the outcome of omega of X is an element of A. Okay, so let's say this is the event. One subset is odd number. When we draw coin, and if it is not coin, dice again. When you draw dice, and when we have 3 in dice 3, then we say this event occurs. This event of odd number occurs, right? Do you understand what I'm saying? So basically F is possible a subset, okay, subset of omega. And when we draw dice, and if that subset occurs, then we say that event occurs, that subset occurs. Then now we can actually define more rigorously about the probability. Again, then probability measure P defined. So I was not rigorous in the previously, but I imply less rigorously. I told you that probability is a function from the sample space, omega, but actually probability is not a function from sample space. Okay, as you said, that is only approximately right. Really, what probability is? Probability is a function from F, function from event, not sample space itself. Probability is a function from a subset of omega to the real number. Okay. Again, in this case, 1, 3. Where is it? This is 1 to 3. Right? 1 to 3 is one possible subset of omega, right? So it is the function from a subset of omega to the real number. So again, let's be specific. Probability is not a function from sample space. It's a function from subset of sample space. And all subset we are considering, the collection of subset we are considering is actually called F. And then one technical condition in probability space, one technical condition is that F should contain null set, empty set, and then it should contain omega. Okay? So F should contain, okay? Should contain this one and this one. That's a basic, okay? So again, the probability of nothing happens, okay, it should be 0. And probability of this happens is, by the definition of, by the second axiom, it should be probability that 1 of 1, 2, 3, 4, 5, 6 occurs is 1, right? And actually this one is from this one, right? This is the, right? This is the probability nothing happens is, right? This is mu union of empty set should be equal, right? Because, I mean, union, no, intersection between empty set and any set is empty set, right? So it means that empty set is disjoint to every set. Because it is empty, intersection with the empty set is empty set, right? So it is disjoint. So P omega U empty set is P omega plus P empty set, right? Because they are disjoint. I think this is important. So let me write down. Let's delete the Felix example. So, right? Right, and then what? We have to calculate this. Then again, this is P omega, right? P omega should be equal to P omega union of empty set. Okay, by the definition empty set, and empty set, since empty is disjoint, so we can decompose each other, and therefore this one is empty, this one, so we cancel each other, so it should be 0. So it is driven from the second and third action. Anyway, f should include, by the definition, f should include this, and f also includes empty set. Anyway, the probability measure is now we have to redefine the probability. Probability is again function from a subset. One of the collection of subset of sigma, which is f. So it is function from f to real number with this property. That is by probability null space 0 or equivalently probability of union of everything. Probability omega is 1. And if A and B are disjoint, okay, A and B are one of the f, one of the subset of omega. Okay, if A and B are disjoint, okay, this is actually slight different way. Then it is 0. If it is not disjoint, we need this part. If it is not disjoint, we can separate A union B into 3 separate parts. Okay, so this is what it says. Okay, so actually this is mathematically equivalent to the second action. We imply this one, and this implies second action. And C, okay, if now we have if they are mutually disjoint, okay, mutually disjoint, then P. Now it is infinity. Okay, infinity. It is more general statement. Any count is called countable. It is infinity, but still we can count. If it is countable union of set, we can it is countable sum of the P. This is my handwriting. You know, while I take this class, I wrote down this one too. So for normal distribution. So normal distribution is like probability thing, right? In case of normal distribution, omega is from minus to infinity. In normal distribution, everything can possibly occur. Of course, for very big number, very small number, that probability close to 0, but still, so that it is possible. Okay? So for normal distribution, 정기분포, okay? domain is minus infinity, and f is all the possible subset of omega, which is called Borel set. I can explain it. P is the integration of this one, about this weird exponential or something like that.